Welcome to the Future of Life Institute podcast. I'm Gus Stocker. On this episode, I talk with Anders Sandberg, who's a researcher at the Future of Humanity Institute at Oxford University. We talk about Anders' upcoming book, Grand Futures, which is a synthesis of many different sciences, physics, biology, economics, as well as philosophy. It's an investigation into what humanity could achieve within the bounds of the laws of nature, and it's really exciting. Here is Anders Sandberg. Anders, welcome to the podcast.
Thank you for having me here.
So you have been working on a book called Grand Futures for a number of years now, and you sent me a draft of it. It's 1,400 PDF pages, wonderful, filled with equations, so much depth there. So my perhaps a bit provocatively, my first question is: does it make sense today to write huge, long books, or is that an outdated form of research?
I think there is a lot of value in doing that, at least for me. I'm learning so much by trying to do this. So, trying to frame what I'm doing is I want to make a map of what we know about the very long term future, how good it could be, how far we can go in different directions. And a lot of that is reviewing existing material that's scattered across a lot of different disciplines and putting it together. But as I do that, I'm noticing annoying holes, problems, discrepancies, and I'm trying to fix it. And that is, of course, research on its own. So, indeed, some of the chapters have become papers on their own. There is one chapter about the longevity of civilizations that also, as a spin off, became material for a chapter in a book on societal collapse. I have a discussion about how long we can make the biosphere survive on, that ended up in an environmental ethics journal. But deep down, you might wonder, couldn't this be done by an AI program? Why do we need a human doing it? So my answer is, of course, it's good for me. I like doing it. It organizes stuff. But it's also that right now we still haven't gotten that effective way of reviewing literature, especially since you actually need to somewhat understand what's going on in order to see what makes sense. Because talking about the future also has this fundamental problem that there are very few facts right now out in the world that tell you whether you're speaking truly about the future or not, which means that it's hard to test. And indeed, there is a lot of blabber. Sometimes it's fiction, sometimes it's just projections onto the future. Trying to figure out what you can rigorously say about the future is a really interesting research project. But in the end, of course, I'm not really expecting a lot of people to want to read that enormously thick tome. I'm going to write the popular version without the equations. But then I can point back to the big pile of papers. If somebody says, Anders, you can't possibly move a galaxy using aluminium foil, then I can bang him on the head with my big book and say, read chapter 26. It has worked examples.
So you have the background book with all of the equations somewhere. You will publish it somewhere, or at least I think you should.
Oh yeah, it's my top priority because I also want to be able to start on other books, but they're building on top of it. Um, I think it's quite important to put things together. As an academic, I'm constantly writing research papers, but a good research paper is about one topic. And usually it has to be a very narrow topic to get through the review process in any academic journal. And certainly, I can write a lot of papers and then pile them up next to each other and say, see, this points make a beautiful line. But it's sometimes better to actually just write the book explaining what that line is, what the things are. And then sometimes it turns out that some parts of that book might be turned into papers on their own.
Do you think there's interesting, we could call it hidden knowledge in between disciplines? So when you combine physics with philosophy or economics with biology, do we discover new things?
I certainly think we discover new things, partially because what is well known in one discipline might be not known at all in another one. For example, there is a set of theorems about reliability of circuits that are kind of in the second or third textbook in reliability theory textbook for electrical engineers. These ones are also applicable for the reliability of complex logical arguments in philosophy. But of course, very few philosophers have done electrical engineering, so they don't even know that there are these theorems that you can apply to look at the shape of logical arguments to get some sense of its reliability. And sometimes, of course, you have information about one thing that exists in one field that is unknown in another field, or methodologies. Computer simulation is a very useful methodology for certain problems. But it's mostly known, of course, in the exact sciences where you can formulate it as math. It's very rarely used in philosophy. But sometimes agent based simulations are a perfect way of demonstrating the logical consequences of various assumptions. You make explicit assumptions, you program them in, and you see what happens. So I do think interdisciplinary work contains a lot of hidden information, mostly because so much information falls between the cracks in different disciplines. One of the biggest issues is that engineers know a lot of things about how to build things, how to move things around practically in the workshop. That is not covered in any of the academic texts. There's a lot of practical knowledge that is quite important. Whether something is easy or hard to do is quite often hard to discover for me as an outsider. I'm peeking into a discipline where I actually need to talk to the people inside to see what actually works. The funny thing is, of course, this also means that I'm getting a tremendous degree of imposter syndrome. I'm writing this extremely interdisciplinary book, trespassing on 100 different disciplines. The good news is that being aware of my imposter syndrome means that I'm now running around trying to fact check with 100 different disciplines and hearing what they say, and hopefully also getting the comments on other parts of the book rather than just the subtopics that I might be starting out the question about.
I imagine it's rather difficult today to get an overview of all of science as I see this book attempting to do. I mean, if you were Aristotle 2,500 years ago, maybe you could know everything that we knew scientifically, but today it seems almost impossible. What have you learned about how much knowledge is out there from writing this book?
So I learned a lot of that. It's very hard to even find what is known in a discipline because, of course, it's very rare that you get a nice list of here are the main facts that we actually know. Even the standard textbook will bring up a few things. Usually, get the slightly philosophical introduction that nobody reads in the textbook, and then the first few chapters outlining the structure. And if you look at the table of contents, you will typically get an idea about what the main topics are. But that's, of course, not all there is to know about it. In mathematics, for example, there are thousands and thousands of theorems that are very important, and many of them have their own names, but you don't know how to find. There is no Google for mathematics. That's one of the uses of AI that I'm really looking forward to. So I can finally ask, is there a theorem that is applicable to this particular case? Now, the thing to do is, of course, to learn a bit about the shape of fields. Different fields have very different methods and different ways of even putting their information into place. Astronomers are living in a world these days of databases. Being very good at managing databases seems to be almost as essential as knowing how to handle a complex instrument. Indeed, most astronomers these days are rarely sitting behind the telescope. They are hunting in big online databases for complex statistical patterns, and they're generally much better programmers than I ever imagined them to be. So I got a lot of very useful tips on Python programming at an astronomy conference this week. Now, the interesting part is, of course, those links and those knowledges between disciplines and the shapes of disciplines, what they know about, what they do, and also what they don't do is very valuable knowledge when you try to navigate between them. Sometimes it's very valuable to know what the border work is, what words and terms to not use to have them take you seriously, because they have decided that we need to have a very firm border against that other pseudoscience field that is not us. Sometimes you want to know that they are using this method and they don't recognize that that applies outside their own discipline. Similarly, knowing where we're overconfident is also valuable. We saw that, for example, in the debates about gain of function research in virology. So there are some people interested in doing experiments that generate pathogenic organisms that could have pandemic potential. In order to understand them better and avoid future pandemics, It's very noticeable that people in adjoining disciplines working on other viruses typically say, oh, that is very scary and very bad. They understand the field well enough, but they also don't have the same investment as the people inside. And I think that knowledge about the shape is useful. So, getting back to the point about trying to cover all of science in a book, it's not just the facts of science or even the big theories of science you want to know. You really want to understand roughly where the different groupings are, what the disciplines are, what their shapes are, and who's talking to whom and who's not talking to whom. And sometimes you find people who don't even know they ought to be talking to each other. And if you create even a slender link between them, you've done something very useful.
I also see you as trying to understand what we can do with the science. So, one methodology you use is this exploratory engineering. Maybe you could explain what that methodology is about.
So, in normal engineering, you create a design to achieve some end in the world, to make a car, to make a computer, to make a light bulb. And then try to make it possible to implement in reality, ideally as cheaply as possible. Now, there are many questions about future technologies that we can fantasize about. We can think maybe we could do this or that. But that is not very rigorous. But you can use the rigorous methods of engineering to actually make blueprints for things that don't exist yet. And maybe will never be built. But we could say, if we do it rigorously enough, that if we ever built a turbine of this size, it would actually have these properties. How do we know that? Well, we know very much about classical mechanics. We know about what works engineering wise. We know scaling laws. Like if I double the size of this thing, it's going to have twice the same area. It's going to have eight times as much mass, and so on. You can apply this to make very reliable predictions about things that you haven't built. And then you can say things like, in this case, it would have a following performance characteristics, which is very powerful for thinking about what you could do with future technologies. Now, the interesting part here is that you can use this to study the limits of technology. And it's, of course, very hard to make a really detailed design. So you can sometimes use a stupid design that nobody in the right mind would build, but it's easy to study. It's a bit like in normal engineering where you don't really know how safe something is. So you add a safety factor of three. You ignore a lot of the fine details about how vibrations and shear and erosion might affect the thing because you just made it three times bigger than what you are fairly confident is safe. So you make something that is a theoretical but also likely to work in reality. You can do the same thing with exploratory engineering. Now, the classic example of this is actually from the British Interplanetary Society. So in 1939, they made a paper where they analyzed how to build a rocket to send a man to the moon and bring him safely back again. 1939. It was based on solid rocket fuel and it had a lot of assumptions which today we would laugh mildly at, but it was a solid engineering design. Then they had to stop producing the journal because of the Second World War. They were kind of busy with other things. But in the next issue after the war, there was an update on this report using liquid rocket fuels because they had seen the V2 rockets falling on London and now knew more about their performance characteristic and could make a better design. This was decades before the Apollo program. And it was most a demonstration that, yes, the laws of physics allow us to construct a system like this. They didn't have any funding, and they could probably not even imagine that the Mayo government would give funding to such a crazy project. But you can still work out the details. Later on, we saw another masterful piece, and that was the work of Eric Drexler in outlining nanotechnology, basically demonstrating and using rigorous chemistry and physics that if you could build these nanotechnological machines, they would have the following fantastic performance characteristics. You would get turbines moving at very high velocity. You could perform chemical transformations that are very effective, computers that are very, very fast, etc. Now, he didn't prove that you could find a pathway from where we currently are to that wonderful world. He has showed that that wonderful world can exist. And then it's up to us to actually find a good development path, which has turned out to be slightly trickier than envisioned in the 1990s. But still, I think it's a solid form of exploratory engineering. So this is how I can be fairly confident that I could move a galaxy using aluminium foil. I can basically outline the way of nudging stars in their trajectories by putting reflectors of starlight and demonstrate that these nudges are enough to make stars change velocity and direction on a large scale, show that this is enough to rearrange a galaxy on another time scale, and that would allow me to use it as a kind of crazy rocket to actually give it a certain velocity. I'm not proposing that this is a good way of moving galaxies. I'm imagining that in some tens of millions of years, when somebody actually seriously wants to do it, they have invented much better methods. But this shows that the laws of physics, as we understand them today, and very, very solid things that we actually know exist, like light pressure, do allow us to perform actions like this.
You're exploring what humanity could achieve if we, so to speak, completed physics, or if we reached technological maturity, as you call it in the book somewhere. Do you think we'll ever reach technological maturity? How fast do you think we'll reach technological maturity?
I think we can be certain we can do wondrous things even without being at the technological maturity. After all, we're doing some pretty impressive things already. If you're not impressed by current technology, just ask one of our Stone Age ancestors, and they would be very impressed by many of the things we have. But technological maturity, it's even hard to define what that means. Does that mean that you cannot invent anything more? Well, you can always try to add an extra fin or repaint it to your spaceship. There is an infinite amount of technologies that you could make, but most of them don't matter. The set of technologies that really matter might be relatively small and finite, and then it might be that we're in a kind of painting and designing them a little bit. But technological maturity also might mean that if you have a need that you need to fulfill, you can start doing that. If there is a machine or a way of solving that need, you will have a way of getting there, and you can do it fairly fast with small resources. Not like the civilization need to drop all what it's doing and spend a lot of time inventing things, but rather, yeah, it's an everyday problem. We can just put our engineer on building it if we then need it. This depends very much on whether the space of possible technologies is impossible to search through. And I have friends thinking either an option is possible. I have some friends thinking that no, we are going to reach technological maturity. Eventually, we're going to know enough of physics that we can just build whatever is needed. And I have other friends saying, no, real technology is combinatoric. We put transistors together into circuits, circuits together into computers, computers together into internets or robots or cars. We actually add new modules, and every new device we make increase them when amount of ways we can put things together. I can put that microchip into a weather station, and now I have a very different kind of design. Automated weather stations, okay, they are now another object I can add to some project. So that means that you get a combinatorial explosion. The first group of friends immediately say, yeah, but the number of truly primitive tools, primitive machines are rather small. There was the famous kind of seven basic things like the wedge, the drill, the wheel. And we have added things. We have electric motor, we have the piezoelectric elements, and so on. We have loudspeakers, we have LEDs. So we have added a few of these basic new elements, but very much smaller than the total set of technological artifacts we have. The interesting thing here is, of course, that combinatorial explosion is not necessarily a problem because you can just do design. So an engineer might decide I'm going to need to make a sound from a machine. So they are just going to get a catalog of parts and look through various forms of loudspeakers and vibrators and other tools. They know that they need a module that does a certain thing, and they know what section in that big catalog to look at. So, in many ways, we have ways of searching for this infinite space of technologies very efficiently. If you set up a project, something like the Apollo project to build, let's say, on the moon base, again, we're not searching randomly here. We are going to have tools and ways of getting the life support system done by the life support engineers, and the solar panels are going to be handled by the solar panel people. So that modularity means that we can rather effectively construct new technologies. We're also, of course, also getting interesting new tools. AI, for example, is allowing us to do optimization of various forms. There are topological optimization methods that mean that you can construct optimal structures and minimizing material use or giving them other properties that are very organic looking, very weird, and can only be 3D printed. But that's easy once you have the right computers and 3D printers. So this back and forth about where the limits of technology go, I think it's going to be very hard to resolve. But I don't really know where I end up in this conversation. I generally think that we're probably going to occasionally find these surprise technologies that are very different from everything else. But most of the technology we do is the easy technology because it's modular. We develop a toolkit for doing it. You can order it over the internet or in a catalog. And actually inventing an entirely new kind of technology is going to be relatively rare. And as we learn more, I think we are going to end up finding that to be rarer and rarer. After a few billion years, I would guess that the rate of totally new technologies is going to be much smaller. We're not going to discover that many of them. On the other hand, for any particular use, you just describe what you want to your AI program, and a 3D printer or matter compiler and makes a structure that solves that problem.
How much of technology do you think we've already invented? So just bear with me here because it might not make sense to ask this question, but just imagine a line going starting in 200,000 years ago with fire and stone tools and so on, and ending in absolutely advanced technology. In fact, perfectly advanced technology. So at the limits of physics. Where on that line do you think humanity is now?
So I think that on a linear scale, we would probably be very close to the beginning. I think we're very, very primitive. However, suppose we use a logarithmic scale instead. So every unit distance was kind of 10 times as much more technology as before. Then I wouldn't be too surprised to find that we would be roughly in the middle. Partially, this is, of course, a bit of just saying it's most likely that you're in the middle of a line than at the end. Uh, but I do think that we have found many of the fundamental ways of interaction with the world. Indeed, when you look at designs for nanotechnology in the Drexler's nanosystems, you find that it's actually a lot of very recognizable things like wheels and the valves. Partially, it's because we know how wheels and valves work, so we can actually make use of that to analyze even a molecular machine quite carefully. And maybe the actual nanomechanisms are going to look utterly different. But when you start looking at the molecular mechanisms inside a cell, you realize that many of them are weird because they're made out of proteins and were evolved rather than designed by somebody who has a limited bandwidth for design. But you still recognize a lot of these motifs. So I think we have found actually quite a lot of the fundamental motifs on how to manipulate the world. There's probably quite a lot of them remaining. I think we're going to find many more. And then, of course, just because you're halfway through this list of motifs doesn't mean that the consequences of technology don't get much weirder. Consider, for example, the transistor. The transistor is a simple thing, yet when you start mass manufacturing it, so it becomes cheap and small, it changes everything. Partially because you can transistorize a lot of electronics. Suddenly, a lot of very disparate designs become possible to do just with transistors. And you can computerize your systems. And suddenly, a lot of the control is just software. And an entire universe of possible programs can be used to run whatever the device is. And that software world has turned out to be much vaster than we imagined when people started out in the 1930s and 40s with the computer science. So while Alan Turing was a visionary and understood that there is an infinite number of computer programs, and also that there are problems that they're not infinite enough to solve, there are many uncomputable numbers. I think he was still envisioning things very much like mathematical calculations and finite state automata moving around. Gradually over the decades, the understanding of what the computational universe was really like grew. So by the 1970s, we had the understanding of computational complexity. We knew that some algorithms run very fast, some are very slow, and there are some problems that seem to be much harder than others. And we could formalize them. We got the classic fundamental problem is the category P equal to the category NP, which is the big problem in theoretical computer science. And we're still making progress in discovering non trivial things in this domain to this day. That was kind of unexpected. This is just what you got from one device, the transistor. It opened up a particular universe. And now, of course, our transistors are much fancier than they used to be. But that extra dimension we got from computation was the really powerful addition.
Do you think we are making differential progress such that our physics, mathematics, computer science perhaps is more advanced than our biology, sociology, economics?
I think it's very much that we're making differential progress, partially because some domains are much harder to make progress in. Physics is potentially a very clean domain. There are general rules, and we can also make very clean systems that follow these rules and analyze them. And the systems don't respond back very much. Well, maybe a little bit on the quantum scale, but generally, the systems don't care that you observe them. This is not true for people. People are complicated. It's not just that they are complicated internally, they are also responding to their own state and respond to the state of others and recognize that they're being observed and quite often try to game the system. Biology is doing somewhat of the same. You both have the effects of evolution having run rampant on this planet for billions of years, generating this tremendous complexity which is just due to trial and error. A lot of that complexity is very arbitrary. You can solve many of the problems in very different ways, but we ended out with frozen accidents. The particular proteins that are now totally foundational to our biochemistry and genetics, they got set billions of years ago, and now you can't change them very much. They could have been different, but now we are stuck with that. On top of that platform, you build this other complex system but a lot of that is artifacts. While there's certainly a convergent evolution, if you're an organism swimming in the sea, having a bright belly and a dark back makes you hard to find for predators from above and below. So both dolphins and penguins do the same thing, as well as various fishes and probably dinosaurs too. But many other things are totally arbitrary, and we end up randomly searching this vast space, which is so vast that evolution haven't got the time to search all of it. Getting back to that earlier discussion about searching through the space of possible technologies, we have some ideas about how to search effectively there. Evolution is myopic and just does nearby stuff. Now, of course, if human biotechnologies come in, the ways things can evolve using technological evolution becomes as arbitrarily tricky as technology is evolving. So, when it comes to our understanding and making progress, I think some fields are just much easier to deal with. Partially, it has to do with predictability. Partially, it might have to do with resources we have for affecting them. Sometimes you have no way of affecting them, like in astronomy, but you have the advantage of living in a transparent universe. So there is light coming in from all directions where you can see what happened in the far past. And now, of course, more recently, we can actually start sending robots out there to poke at some nearby things. So that kind of window of opportunity exists in some disciplines, but not in others. So the problem here is we might end up having a grand unified theory of physics, but we're still not going to be able to say everything about biology simply because there's a lot of random stuff that could have happened differently. There might be windows inside complex fields. Evolution allows us to understand roughly what's happening in a lot of biology, but quite often you get weird complications. Similarly, supply and demand makes a lot of economics make sense. It's a very simple and very robust rule, except that there are some cases where there are interesting exceptions, and you can't use just supply and demand to figure out what to do with your monetary policy. Probably. I'm lousy at economics. I find it way harder than quantum field theory.
In the book, you often resort to physics and computer science, chemistry, and anything where we have precisely defined equations. And I think that's useful because what you're trying to do is delineate the limits of what we could do. And so we should talk about what your conclusions are about this question of how big the future could be, how grand could the future be. There are various different scales to measure how big the future could be, or there are various aspects of the future to be interested in. I have a list here. For example, how materially wealthy could humanity become?
Yeah. And just getting back to your intro here, it's worth noticing that these physical boundaries, they are simple to analyze. We can do a lot of stuff inside that, but that's going to be culturally determined. And I can't predict culture. Nobody can, because, well, it's full of people inventing reasons to do things, especially, and many of these reasons are nobody has done this or nobody has predicted this. I'm going to show off my free will by doing something totally different. So looking at boundary conditions from physics is useful, but that's not going to tell us, of course, that we're going to be moving up to them. But when we think about material wealth, the basic issue is how much stuff can we get? And there is, of course, an obvious thing about where the stuff is located in the universe and how easy it is to move around. But from an everyday perspective, how wealthy would you actually want to be? And I wouldn't be too surprised to find that a million years from now, people are not owning more matter in the practice than we are doing it right now, because we don't really care too much about matter. What we want is a delicious meal. What we want is a nice house that looks really good and our friends like having a party. And we want many of these things that our matter is just one way of providing them. You could, of course, say maybe we can all move into virtual reality and get it with a minimum of matter. But even if you say, well, we want to have actual real matter buildings, a lot of those problems are manufacturing problems. The reason it's expensive to get a house right now is to a large degree that you need to make a house. And right now, you need people to make it for you. You need the architect to make blueprints. You need builders to build it. You need people to make the component parts. And you need an interior designer or decorator to put up a lot of the small details. It looks very much like we can automate most of this. That's a general pattern you see in exploratory engineering. But once we understand how to do something, we can typically automate that process. And then it becomes orders of magnitude more cheap or more efficient. Making houses by hand is much more expensive than using the standardized components. If you have a 3D printer for buildings, then it becomes even cheaper. Of course, that 3D printer might still be expensive, but you use it for a lot of buildings. So it looks like, in terms of material standards, we're probably going to end up way wealthier than now. Now, there is two interesting issues here. Most of that wealth is probably more in the terms of services than stuff. And second, of course, what we care about now is also a new dimension. That's sustainability. So our medieval ancestors might have wanted to have as much gold as possible and as big warm houses and as much food as possible. And we would probably say today, yeah, gold is not a really great investment. And having a big house, yeah, that's kind of nice, but it's also slightly impractical if it's located in the wrong place. And too much food. Well, have you heard about the obesity epidemic? Actually, we changed what we care about. We want healthy food. We want ethical food. We want food with a nice story and going by about that this is locally sourced or that this is a particular old family recipe. As you get wealthier, you switch more and more to post material values. This seems to be a generic thing we see in human cultures. But from a practical standpoint, I think we're going to be using manufacturing systems like nanotechnology and biotechnology and robotics to get both the material wealth and a lot of service wealth.
If we're thinking at the limit of material wealth, could it be the case that we actually become more interested in matter as time goes on? Because we are reaching the physical limits of what can be done, say, with 1 square kilometer of space on Earth. And so the only way for us to improve, expand, whatever it is that we want to do at that point is to acquire more material resources, for example, by space travel.
So one scenario might be that in the future, when the majority of humans upload themselves and live wonderful lives in virtual reality, but that still needs to run on computers. Somewhere you need to have your data center. That data center is going to need electricity and it's going to produce waste heat. And it's kind of interesting to note that a lot of the conversation about material wealth hinges on, can we get cheap energy? And the problem here is, if you want cheap energy, well, the main source on Earth for cheaper and renewable, sustainable energy is sunlight. Wind is essentially a derivative of sunlight and much smaller. But sunlight only impinges about 1 kilowatt per square meter at best. So you need a lot of area to do that.
So you're saying that we need a lot of area to produce energy using solar energy, but what about the alternatives here?
The alternative is to use some form of nuclear energy, which can be much more intense and have a lot of other important advantages. So while I'm all in favor of having a lot of solar, nuclear is very good for at least base load. And in terms of amount of energy you can get per unit of area, it's much more powerful. You need to obviously solve issues about safety and the non-proliferation of nuclear weapons, but I think those are doable, and I think people have been too pessimistic of trying to actually resolve this. I think one can do quite well with nuclear energy, not to mention fusion power if we get that working. But the problem here that is really serious is waste heat. So imagine this utopian future. We have closed the last fossil fuel burning systems, but we're using enormous amount of energy from solar panels and nuclear. Where does the waste heat go? Well, it's being radiated away into space, of course. And here's the problem that radiation happens at the top of the atmosphere, and we only have a finite surface area of the atmosphere. So if we were to increase our energy usage by about a factor of 100, even if it was perfectly carbon neutral or carbon negative for all of that I knew, we would still start heating up the planet. Simply because the planet has a finite ability to dissipate energy. Indeed, this is a fundamental limit even on how many people you could have on the planet. There have been this ongoing discussion about what the upper limit of human population could possibly be. And there is a fun paper from the 1960s calculating an upper limit to 10 to the power of 16 people, because beyond that point, the total body heat of these people is just going to be too much to radiate away into space. At that point, of course, Earth is just a big machine for having people in it. It's very dissimilar from what anybody probably would want to actually have. Although that paper also happily pointed out that you're going to get a million Einsteins at any point in time, not to mention even more Beatles. The author was clearly not a fan of Beatles music. But the interesting part here is heat dissipation is one of those really fundamental limits that actually affects quite a lot of the grand systems I'm talking about in the book. Turns out that for computers, it's the same thing. If I erase one bit of information, that information has to go somewhere. Otherwise, I have kind of reduced entropy. So the entropy needs to go somewhere. And typically, that means heat needs to be dissipated. So a really, really powerful computing center needs to radiate away the heat in some way. And in space, of course, radiating away heat is tricky. Yes, the cosmic background is 3 degrees Kelvin, but you still need to use infrared light, and that's very inefficient. We are kind of used to living surrounded by an air that can convect away and waste heat very cheaply and easily, and we never think about where that waste heat eventually goes at the top of the atmosphere. But for very powerful systems, you might actually have to think about this. And that goes also for manufacturing. So if you imagine a matter compiler that can just magically rearrange atoms into whatever you want, sounds like a wonderful thing until you realize that if I can rearrange atoms, entropy plays a role. I get waste heat. So if I just completely rearrange them, it actually runs on quite a lot of megawatts of power. Oh, that's going to be hot. That's going to be much worse than the fridge in the kitchen. So actually, you want the transformations to be slower. You want them to not release as much waste heat by being more careful about what molecules you move around. So precision is really important. The reason organic life can build so much stuff without running hot is that it quite often uses isentropic processes. There is very little real dissipation going on. And this is something that we obviously might want our own manufacturing methods to do so they don't waste too much energy and also don't produce too much waste product. At the same time, we might still want to speed things up compared to biology because biology is rather slow. If we have to wait a season for the next crop of cell phones from the tree, they might be obsolete by that time.
How much of the grandness of the future or potential grandness is dependent on humanity leaving Earth or leaving the solar system and populating space?
Well, that depends a lot on what value you put on the spreading, but also maybe on survival. So, if we humans live here on Earth with perfect sustainable energy and all of that, the normal lifespan of a species is about a million years. So you could imagine this kind of humble utopia and that is sitting there and then going extinct after a million years. That's still a lot of future generations. It kind of vastly more than currently have ever lived. But an advanced society should be able to handle existential risks. Indeed, even surviving for 1 million years means that you actually are pretty decent at handling normal risks, at least the ones you cause to yourself. But you would also probably be able to deflect a bit of asteroids and take cover when there is a supervolcanic eruption, which means that I think it's a fairly good chance that if we survive that long, we could also survive mass extinction level threats. That would give us hundreds of millions of years, probably up to the natural end of the biosphere. But in about a billion years, the biosphere is going to likely crash because the increased solar input is removing carbon dioxide from the atmosphere, and eventually photosynthesis is not going to work. And at that point, the biosphere dwindles and also the thermostat of Earth starts breaking down and eventually turns into a rather nasty desert world or a hothouse like Venus. I think we can intervene and fix this, and then add billions of years to the biosphere, which I think, from even from a purely ecocentric perspective, that doesn't care about humans but only ecosystems, is a good thing to do. Yet, if we just moved into the solar system and made self-sufficient space habitats, which I think most people would agree is technically doable, maybe not right now, but if we put our mind to it over the next few hundred years, we could do that without being too stressed out. If you can mine asteroid material and turn that into the tools and the contents of your biosphere, you get energy from sunlight, you can recycle material well, you have enough surplus so that you can build new habitats and people can reproduce in them. That would mean that humans could just settle the solar system and you could have a population of trillions of people. That's it, not even assuming anything grand. Not like these beautiful pictures from the 1970s from NASA. They're showing the rotating O'Neill habitats. This is just crappy International Space Station versions. We can probably aim much higher than even the grand visions of the 1970s. But my point here is, if you actually can find this ecological niche, taking essentially asteroid material and sunlight and turn that into biospheres, which I think very few people think is physically impossible. The biggest question mark is actually whether humans can reproduce in space. That's the one big question mark we still have. Then you end up with a population that can survive for at least 5 billion years until the sun turns into a red giant. That's 5 billion years of perhaps a trillion sized population. That's a lot of future lives. Getting to other solar systems is harder. And this is where we get to the question, is that a grand future for humanity as we know it? Because the most obvious way of getting to another solar system is to send robotic probes and maybe build things over there using robots. And maybe they can have biological samples and rear kids with nanobots, but no adult human has ever traveled between the stars here. You just get humanities popping up at other settled systems. Or, as I think is more plausible, we eventually learn how to scan a brain, make a neural network that you can run on a computer, and you have virtual people going over there, and maybe then turning biological if they want to. Now, if you can do this, then at least the galaxy is available, and we should expect humanity to survive for a few trillions of years at the very least, because that's as long as the stars are going to last.
It's a very interesting discussion of what counts as humanity. I don't expect there to be a factual answer here, but it's something that we should think about morally. What it means for humanity to survive.
And that is part of the grandness. What is the value? Because I can already hear a critic saying, yeah, but having more people for millions or billions of years, who cares? And that's a good point. What is so good about having people around for a long time? Indeed, we can envision ways of surviving much longer beyond the end of a lifetime of the stars. After all, there are energy sources that could tide us over in the degenerate era that's much vaster, far beyond this.
What is the degenerate area? Oh, era. Sorry.
So right now we're living in the stelliferous era where there are stars shining. But we're approaching peak star in a few tens of billions of years. Beyond that, the stars are going to slowly dwindle. But red dwarf stars last for literally trillions of years. Um, but in about 100 trillions of years, there are not going to be much stars around. Yet there's going to be quite a lot of resources. There are still brown dwarfs that contain a lot of hydrogen. There are black holes that you can dump, for example, remnants of old stars into and extract even more energy than the star produced during its shining lifetime. So you could definitely imagine that life and, well, technological life could survive in this era and actually thrive. Indeed, if you happen to be uploaded in a computer and care a lot about saving your energy for computation, the colder it is, the easier it is to do computations without having to dissipate too much. So this might be the time where all the really big thinking of the universe actually gets done because it's too hot right now here in the early spring. But eventually you run into various problems. Some of them I think you can solve practically, like galaxies would tend to dissolve because of random interactions between stars, throwing some stars out of a galaxy and others into closer and closer to the central black hole. I think that can be handled by a bit of interstellar traffic control. But somewhere north of 10 to the power of 36 years, proton decay is likely to set in according to most theories of physics. Our kind of matter is very likely to slowly disappear. And that's probably curtains for our kind of life. But the real question is, of course, what is the value of surviving up until that curtain time? And you could say that, well, maybe life's meaning is life itself. Staying alive is what living beings are all about. We're trying to make sure we stay alive or our offspring stay alive. So keeping this unbroken chain going has some special value. That is what the kind of beings we are. Others would disagree and say, no, 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 I'm totally fine not having any kids, but because I want to spend my life in contemplation about higher things or help others and do other things. Maybe the unit of selection is civilizations or chains of civilizations or actually doing other things. Because maybe some philosophers would say once you figure out the really important stuff, there's nothing left to do, and then you should just end over there. You have quite a lot of different theories depending on different theories of value and philosophy about what we ought to be doing with the universe. But I can at least give some of the boundaries like, okay, you want to survive to the degenerate era. Here is what you need to solve before that. So you want to do this big computation. Well, now you need this many galaxies worth of matter, which means that you need to set off rather soon because in about 300 billion of years, all the other galaxy clusters will have moved away across the cosmological horizon. So you can't get them if you wait too long. So you need to hurry up a little bit. So we get these interesting boundaries. But the really interesting thing is what actually happens is, of course, unpredictable, but we can start thinking about the moral hedges and trades we want to do. There are going to be people who want humble futures. They just want sustainability. They want to preserve a natural biosphere and don't want to do too weird things. They might be the Amish of the future. And ideally, just like the Amish are protected by living in a decided non humble surrounding society, we might imagine having a deal that, well, the post-humans doing stellar engineering and weird things have a deal with the stay-at-homes to leave them in peace and quiet, and vice versa. And similarly, the nerdy and the super post-humans that want to run a lot of computation, they are just going to be sleeping up until 100 trillions of years of time. Then they take over the universe. But the people who think that it's more interesting to do things in the young spring of the universe, they are playing around for the first few hundred trillions of years. So you can do all sorts of interesting trade-offs, and we can start thinking already now about some of the politics and how do you make contracts that stick over a long time. That would be useful also, of course, with dealing with our own current governments. We want to figure out ways of making business contracts and the institutions that last for a long time. So many of these questions, when painted cosmological, sound like very grand science fiction. But I do think many of them are also very relevant things to solve here and now.
We can also think about which moral theories are the most greedy in a sense, where some moral theories will be more maximizing than others. For example, you might want to have a humble utopia that would be enough on some moral theories, whereas on other moral theories, we might want to spread into the universe and populate it with lots of conscious beings experiencing the heights of what can be experienced. And so, do you think that perhaps destroys our or hampers our ability to do these trade-offs if some moral theories are much more greedy than others?
I think it makes the negotiations more complicated because maximizers will quite often be bad neighbors to the satisficers who are satisfied. But even there, you can probably find solutions because the satisficer might say, yeah, if you actually start taking our stuff, we're just going to blow it up, and then you get nothing. And the maximizers might notice, yeah, those satisficers, they're so annoying. They're actually serious about this. Okay, in that case, it might not be worth quarreling with them. I think there are interesting problems here because there's some maximizers that can play along with each other rather well. You could imagine the happiness maximizer that wants to pave the universe with happiness generating states. Maybe they have found some very, very blissful little mental state in the mind of a rat, and they just want to make Dyson sphere after Dyson sphere full of these states repeating forever, that discovery of a perfect piece of cheese forever. Meanwhile, you have a bunch of other the knowledge and thought maximizers who think that's utterly ridiculous. We want to think deep thought. We want to solve the fundamental problems of philosophy, mathematics, and whatever is beyond. And they both want to build bigger computers. So they might now say, okay, or we can't. If you can't hack each other, what do you do? Well, you can just agree to disagree and hope that gradually convince the other side with good arguments. Because there is an important question about how much does it cost to have a conflict and how much does it cost to negotiate. But of course, the deep thought maximizers have an interesting problem. They want to have their deep thoughts communicated across the society, probably because some of the thoughts might be so deep and so big that you need a lot of minds to do. So they need to be causally connected. Meanwhile, the happiness maximizers are going to say, actually, the happiness on one server is totally independent of the happiness of another server. We are, of course, very into making sure there's as many servers as possible, but they don't need to be in contact with each other. At that point, the deep thought maximizer might say, yeah, so let us take over the next 20 megaparsec of space. We're going to move the galaxy clusters together and build our grand academy of deep thinking. But the rest of the universe is useless for us because we can't move those galaxies back into our academy servers fast enough. The expansion is always going to win out, and in that case, why don't you take them? You are not going to get the next 20 megaparsec, but you're also not going to have a quarrel with us. We're going to defend our servers, but you get all those gigaparsecs of stars to turn into those very blissful rat happiness emulating servers. That might be a solution. And hidden inside, almost like one of those little imperfections that make the crystal grow, is a little planet named Earth, where is a lot of traditional humans having tea and playing cricket and wondering why the sky looks so weird.
What I hear you doing here is thinking about how all moral theories postulate something that's valuable, but whatever they postulate as valuable, it will depend on the underlying physics. And so, therefore, we can say something about it when we're thinking at the limits of physics. So, in this sense, physics informs our morality.
I think it informs us about our options, and ought implies can, as Kant famously said. If we find that we cannot do something, then we shouldn't do it either. So it might be that there are some of these grand futures that, because of unknown physical reasons, actually they cannot be implemented. In that case, we have a good reason not to pursue them. Sometimes you might say, yeah, we can satisfy it. We can do an approximation. Maybe that's the best we can achieve in this fallen, imperfect world. There are also some issues that happen that some theories are similar enough that they might still be competing. You could imagine, for example, the radical negative utilitarians that think that happiness, that's nice, but pain is bad. We need to really make sure that there is no pain anywhere. And they might be the really annoying neighbors because they might say it's actually not a problem for us that if we get less resources, if we destroy your resources, because you might be generating painful states. They might be very good neighbors to those happiness maximizers that just run servers full of that eternal blissful moment, but they might be super annoying neighbors to other values. So it's not given that just physics is going to resolve our moral differences. But I think we're going to find that with some directions where we can actually make a typology and figure out where there are likely conflicts and where there might be good compromises. And the funniest part here is that some of it is set just by the light speed limitation, the expansion of the universe, the way information interacts with entropy. This physics actually gives us some of the marching orders for our research into value theory.
I thought I had a very smart objection to your thinking about grand futures at the limits of physics, which is just that our physics has evolved so much over the past 100 or 200 years. So there must be unknowns that will affect what we will think of as physics in the future. Perhaps some of the fundamentals of physics will change. Then it turns out that you have a whole chapter in your Grand Futures book just dedicated to answering this question. So perhaps we could end by talking a bit about some of the unknowns of physics. How could things change, and how does this affect our ability to predict how grand the future could be?
Yeah. So it's pretty obvious that we have had physical revolutions where we understood the world in a better way. And many of them have totally upended not just a little bit of the formulas we use, but even the ontology of what's actually going on. When we ended up with relativity and quantum mechanics, our understanding of what kind of things actually exist changed rather profoundly. Yet the clocks over in Switzerland didn't stop working when Einstein formulated his equations. It's just that now we understand time much better and we can make somewhat better clocks. So, on one level, the normal reality we have must always be compatible with whatever we find in new physics. It just might be that we realize that actually what really exists in the universe might be a handful of things that are actually quantum fields playing out on some kind of weird space-time manifold. There actually doesn't exist coffee cups and planets, but there are excitations in complicated fermionic matter fields, which is a mind-boggling truth, but we still make coffee normally every morning. So the real problem might be that some important aspects of these theories that change the direction turn out to be wrong in our understanding. We have this term, the crucial considerations at the office. It's a bit like when you're out in the forest and navigating by a map when you realize you've been holding the map upside down. That piece of information suddenly changes your strategy completely. So it might be that there's something we find out about physics that might change things. Now, it could be that general relativity is wrong. Indeed, it's not implausible that maybe the Einstein equations are the first order terms of something that is an infinite series of something. But we have a lot of constraints on that, and it's not going to matter very much, at least in the world of stars and planets and maybe even normal cosmology. But it might allow us to do very strange things close to black holes or wormholes or whatever. Quantum mechanics is even more interesting because it seems to be fairly rigid. You have a few axioms, and if you nudge them even the slightest, things break very badly. It's almost a brittle theory. While you can kind of change things around a little bit in general relativity, that is still allowed. Quantum theory is much more rigid, which doesn't mean that it couldn't be that very, very weird things going on anyway. To me, the most important part is, do we understand the physics of information well enough yet? And I don't think we're there yet, but it almost feels like we're approaching some kind of unification. So we have a Landauer principle of linking information erasure with thermodynamic dissipation, which is kind of crucial way for me to constrain what advanced civilizations can do. Because as long as I can reformulate that as information processing, I get a bound on how much energy they have to play around with. But if that turns out to be wrong in some sense, or that we have a better way of understanding information that links with quantum field theory, that might change things. Although I bet that eventually we're going to find more constraints rather than fewer constraints. One of the big bounds in my book is because of how much you can pack information together. It turns out that quantum field theory hints, together with the theory of black hole entropy, that there is an upper limit on how much information you can squeeze into a region of space-time. Basically, in order to store the information, you need a quantum field that varies. If it varies a lot, you get a lot of energy. That bends space-time and eventually it turns into a black hole if you try to squeeze up too much information. These are still somewhat informal ideas. It's not really truly proven, but it might very well be that we have a fundamental bound here on how much performance you can essentially get out of anything in the universe as a computational system. Now, that is a very important question mark for me. But on the other hand, there are the unknown unknowns. Maybe there are new kinds of matter, maybe new forms of force fields. That probably doesn't matter very much in everyday life, but it could be just like the semiconductor properties of silicon are really, really modest things. We don't really notice it. But when you arrange silicon atoms in the right way, you get transistors and computers and the internet revolution. And suddenly, that very small property of a otherwise relatively normal element changes everything. And maybe it turns out that there is a fifth nuclear force, and most of the time it doesn't do anything interesting, but we eventually figure out a way of tweaking it to do amazing things. This is very hard to predict. On the other hand, you can also play around with things like, what about faster than light travel? We can kind of go through the wish list of science fiction tropes and see what happens if they're true. And if you get faster than light travel, basically you also get time travel. They're equivalent. And this is already a bit troublesome. So the Fermi paradox, where are the aliens, suddenly got much worse because now you could get visits from aliens, not just from anywhere in the universe, but from anywhere. And of course, the normal time travelers from humanity's future. And then you realize that actually they could bring back computational results. You can do computations using time loops. And that turns out to explode the computational power of computers enormously. Indeed, classical and quantum computers become equivalently super mega powerful. And at that point, I need to leave off that discussion of the book by saying, okay, if you have faster than light, you get these results. Uh, I can't really imagine much about this weird universe where super intelligences that are way more super than I normally would imagine super intelligence that from the end of time can literally send you an email and affect their history. It's a very weird universe. Doesn't mean that it's necessarily impossible, but it's so different from the universe we think ourselves living in that we probably shouldn't be spending too much time evaluating it, at least up until the first email from the far future shows up.
Fantastic, Anders. Thank you.
Thank you.
That's it for this episode of the podcast. On the next episode of the podcast, I talk with Anders about the value of the future. From which perspective should we evaluate the value of the future? And how valuable could the future be?